In the previous lectures, we talked about different modulation schemes and error calculation for those modulation schemes. And by visualizing the error formula derived for modulation schemes, can we say communication can be made completely error-free? So, if we want to achieve error-free communication, we need to check the ratio EB by N naught. If we want error introduced by the system should be 0, then this ratio should tend to infinity. To do so, either EB, that is energy per bit, is tending to infinity, or noise introduced during that bit duration is 0, or both. Now, if we talk practically, can we have any control over the appearance of the noise? No. Noise is random in nature and we cannot govern its presence at any moment of time. So it cannot be made to 0. Similarly, is it feasible to introduce infinite amount of energy with the signal during the bit duration? Obviously, it is not possible. Practically in the lab, we cannot have this kind of facility to introduce infinite amount of energy with the signal. This can also be achieved by decreasing the data rate to make energy high is another possibility, but it is also not acceptable in present scenario because nowadays we need to have high and high data rate. So practically EB by N naught can be made large but not infinity, and hence error-free communication is not possible. Or in other words, we can say communication can never be error-free. So, it was earlier perception that we cannot achieve error-free communication. In 1948, Claude E. Shannon proposed that if the information rate is less than the channel capacity, then we can have error-free communication of information. This was certainly a revolutionary result. So for a given channel capacity, if this condition is followed, then we can have error-free communication of information. But here he talked about error-free communication of information, but not error-free communication. So further, we have to emphasize on this word information. So this was considered as a very revolutionary result and against the common sense too. We are not having the ratio EV by N naught tending to infinity. That is, error is not achieved to be 0, but still we are able to say that we have error-free communication. This is considered against the common sense at that time. But here we should understand that we are not talking about signalary rate or pulse rate, but information rate. A statement by Claude E. Shannon was not considering the pulse rate, but information rate. So we need to differentiate the pulse rate by information rate. The question comes in our mind, what is information? If we follow intuitive way to understand the information, then we can say that if more surprise is associated with any message, then it contains more information. Or if probability of occurrence of any message is less, then it contains more information. So if probability of occurrence of any message is tending to 0, then its information content is tending to infinity. It means there is some exponential relation between the information and probability of occurrence. Thus we can say information is proportional to log of inverse of the probability. If we take an example and I say in cricket match, Australia beats Zimbabwe, you will say, okay, this is usual. But if I say Zimbabwe beats Australia in a cricket match, then you will be amazed and you will ask for the news or start searching internet. This example shows that the message with more surprise is containing more information. If we describe information in engineering way, then we can say that information content in a message will be decided according to the time required to convey the message. More the time required to transmit or convey the message, more will be the charge. Thus, the engineering way depends upon the usage of system or channel. If channel is used for more time, more the information conveyed and thus more the user will be charged. Let us understand the concept of information with Morse code. In Morse code, information is transmitted in the form of dots and dashes. The question is, how can we assign the codes to the various alphabets? For efficient transmission of the information, we need to assign small length code to the more frequent letters. For example, vowels, and large length code to be associated with the letters occurring rarely like Z, Q, X, etc. This technique is adopted to transmit more information within the given time duration. Frequently occurring letters are less surprising, thus associated with small length code, while rarely occurring letters are more surprising and hence embedded with a large length code. Here we conclude that something which is not surprising is more probable. For example, its probability of occurrence is high. Consider the case that we have two equally likely messages M1 and M2 and they are encoded with 0 and 1. It means by 1 bit only. Since they are equally likely, their probability of occurrence is half and amount of time required to transmit any of these messages will be 1 unit time. Take another case, there are 4 equally likely messages like M1, M2, M3 and M4. 2 bits are required to encode these 4 messages and thus 2 units of time to transmit any of these messages. Probability of occurrence of each message is 1 by 4. Now consider we have n equally likely messages. We require log n base 2 number of bits to encode each message and log n base 2 unit of time to transmit each message. We are taking base 2 because we are thinking that we are encoding the messages in binary. Probability of occurrence of each individual message then will be 1 by n. Now we can say that the amount of time required is directly proportional to the number of bits to be transmitted. Or in other words, information content is directly related with the number of bits associated with the message. If we have n messages and we require log n base 2 to encode each message, then information is directly proportional to the log n base 2. It means information I is equal to k times log n base 2. Now as we know probability of occurrence P is equal to 1 by n, then information is equal to log 1 by P base 2 bits per message symbol. Here proportionality constant K is normalized and taken to be unity. So we can say it is directly equal to log 1 by P base 2. From here, we can define that information I is termed as minimum number of binary digits required to encode the messages. A very popular term you heard in thermodynamics is entropy. Here in information theory also, we define this term entropy as average information emitted by source per message symbol. This entropy is an attribute of information source. Now consider a memoryless source. Memoryless source means that the current symbol is not generated on the basis of previous or next symbols. That is, current and previous informations are unrelated. In short, we can say all the symbols are statistically independent symbols. Suppose we have memoryless source and generating M messages M1, M2 to Mn with the probability associated with them are P1, P2 to Pn respectively. In this message sequence, the information content with any message symbol Mi will be equal to log P1 upon Pi base 2. Hence, the average information per message symbol will be given by total information divided by number of symbols. That is summation I equal to 1 to n log 1 upon Pi base 2 divided by n. Since n is equal to 1 by p, thus average information of the source will be the summation I is equal to 1 to n pi log 1 upon pi base 2. Hence, average information emitted by the source depends upon the probability distribution of the various message symbols, and this is called as entropy of the source. And thus entropy of the source is equal to the summation I is equal to 1 to n pi log 1 upon pi base 2. It is important to note that information and entropy are the attributes of the source itself. First, we will analyze the discrete source because of its simplicity. Basic details and concepts will also remain same for the continuous sources. Consider a message source M with M1, M2 to Mn messages and probabilities of their occurrence are P1, P2 to Pn respectively. Entropy of this source is Hm, which is conveying average number of bits required to encode the message. Consider a message sequence of length n. Here we assume that value of n is sufficiently large and message appearance in a sequence is random. In this n symbol message sequence, messages M1, M2, etc. are occurring randomly. The question arises how many times M1 message appeared in this sequence. If we know the probability of occurrence of message M1 by the source is P1, then we can say that message M1 occurred n times P1 in the sequence. Similarly, message M2 occurred n times P2 in the sequence and so on. Now we call this message sequence Sn, and since the occurrence of all the messages by the source is random in nature, then probability of occurrence of this specific sequence is P of Sn, and it will be equal to the P1 to the power n times P1 and P2 to the power n times P2 and so on. This generated sequence consists of number of independent emitted symbols. Therefore, probability of this type of specific sequence is the product of probability of the events. Since number of messages in the sequence is very large, then probability of occurrence of all typical sequences will be same. This means that even if we do not have a equiprobable source, we can construct a new message source which is equiprobable. Here, new equiprobable message source do not emit single symbol, but a sequence of n symbols where n is very large.
As per source coding theorem, to encode a source with entropy Hm, we require at least Hm bits per symbol. In other words, we can say that if we have any encoder, then minimum number of bits required to encode the message generated by the source will not be less than the entropy of the source. And these minimum number of bits are achieved if the source is equiprobable. So in other words, we can expect our optimum source coder to produce an average word length equal to entropy. Source coders are basically the devices which are used to assign digital representation to the messages generated by the source. For example, PCM, pulse code modulation, delta modulation, etc. But we have to check whether they are optimum or efficient source coders. In this process of checking, we need to compare the average length of the code word with the entropy of the source. Less the difference between the average code length, better the source coder. Now, if we have a non-equiprobable source coder, then surely average code length is more than entropy. If we want our source coder to be optimum, we need to convert it to equiprobable source. But practically it is not possible to have length of sequence n tending to infinity, as coding delay also becomes infinite. It simply means that we need to wait for sources to emit infinite number of messages and then start the coding process. If we take an example of speech coding, a person on the other side need to wait for such a long time to listen the voice. So we need to think of other practically feasible solutions in which coding delay is less with better code efficiency. Or we can say that we need to find a coder which can give us better coding efficiency but with tolerable amount of delay. Huffman suggested coding method to generate optimum source code. This source coding method is applicable to memoryless sources. In this process, coding delay is unity, which means that messages are encoded as soon as they appear. Encoding means assigning specific digital representations or value to each symbol generated by the source. Now, as per Huffman coding, we first arrange the messages in the order of descending probability. Then we combine the last two messages into one message. Again, we arrange rest of the messages in the order of descending probability. We repeat this process until the number of messages reduce to 2. These two messages are now assigned with 0 and 1. 0 to first message and 1 to second as their first digit in the code sequence. We now go back and assign 0 and 1 as second digit for the two messages that were combined in the previous step. We keep regressing this way until the first column is reached. This code is finally obtained. The efficiency of any code can be defined as the ratio of entropy of the source to the code length. Efficiency of the code will be always less than 1, as the entropy of the source will be always less than or equal to the code length. And redundancy will be equal to 1 minus efficiency. More the redundancy indicates less efficient the code is. Now consider the given example. First of all, the messages are arranged in the order of descending probability, and the process is followed as conveyed earlier. The beauty of Huffman code is that it is a comma-free code. The messages are encoded and transmitted without providing any message separator. Huffman code can uniquely decode even though there is no marker between the codes. This can be taken as an exercise by taking different transmitted code sequences and try to decode it. Suppose M1, M5, M2, M1, M4, M3, M6 and so on are transmitted in a sequence. And as we have taken the previous example and we have just the sequences and encoded it, using that we can encode this message sequence as 0011, 01, 0001, 10, 1011. The person can verify that this message sequence can be decoded by only one way, even if there is no demarcation between individual messages. Now, if we try to find out average length of the code, then it comes out to be 2.45, and entropy can be calculated by the formula as 2.418. The coding efficiency will be calculated as 0.976 and redundancy as 0.0024, which means while encoding the messages, 0.0024 bits are redundant bits and added with the messages. Huffman coding is an instantaneous coding and more popular because of its simplicity. If we want to achieve higher efficiency, we can compromise with the coding delay. That is, by taking 2, 3 or 4 symbols at a time and encode them. This process is known as higher order Huffman coding. Suppose we take a source generating only two messages M1 and M2 with probability of occurrence 0.8 and 0.2 respectively. As the message is encoded with 0 and 1 using the Huffman coding procedure, we can easily calculate and find the entropy of the source to be 0.72 and thus the redundancy is 0.28. Let us consider second order Huffman coding and think of a source which is generating two successive codes of the previous source. Let new source is having four possible messages M1 M1, M1 M2, M2 M1 and M2 M2 with the probabilities of occurrence 0.64, 0.16, 0.16 and 0.04 respectively. As per the Huffman coding procedure, all the four possible messages are encoded. In second order coding, average length of the code is calculated as 1.56 bits per symbol. As this average word length is for two messages of the original source, the average length of the original source will be 0.78. Hence, code efficiency can be easily calculated as 0.923. Now let us take an example for third order Huffman coding, and we can think of a source which is generating three successive codes of the first source, previous source. We can find the codes by the following the same process of Huffman coding. Average length of the code generated by third order Huffman coding is 2.184. This is the word length for three messages of the original source. The average length of the original source becomes 0.728 and hence code efficiency comes out to be 0.989. We had seen that as the order of coding was increased, efficiency of the code increases, but also the coding delay. So Huffman coding beyond third order is not used in practice. Thus there is always a trade-off between the coding efficiency and coding delay. The idea of source coding is to increase the code efficiency, in turn reduce the redundancy to avoid the burden on the channel. Let us summarize what we have learned in this lecture. Entropy will be maximum if source is generating equiprobable messages. But most of the natural sources are not equiprobable. If we want to make the source to be equiprobable, then we need to club n messages. When n will be large, then the new source, which is considered as generating the sequences, becomes equiprobable. By making the source equiprobable, actually we are increasing the coding efficiency but at the cost of coding delay. In practice, large coding delay is intolerable. So we need to have some trade-off between coding delay and coding efficiency. In other words, we should have some optimum source coder. Huffman suggested comma-free instantaneous coding technique but at the cost of coding efficiency. It means some redundancy is still there with the code. Higher order Huffman coding can be used to increase the code efficiency but compromising with the coding delay. In practice, Huffman coding is not used beyond third order.